start then. So it's a great pleasure to have Hee-Cheol Kim from POSTECH, who will talk about 3D topological phases from M-theory. And please, everyone, if you have a question, unmute yourself and ask or type it in the chat, and then I'll tell Hee-Cheol about it. So please, Hee-Cheol.
Okay, so I'd like to first thank organizers for giving me this great opportunity to present my work in this seminar series. So today I'll talk about 3D topological phases from M-theory, and this talk is actually based on my recent work with Professor Girang Cho at POSTECH and Dongmin Gang with the string theory group leader at APCTP. Okay. Yeah, topological quantum theories, quantum field theories are very special field theories whose correlation functions are independent of the space-time metric. And it describes low energy physics of topologically ordered states having mass gap and vanishing Hamiltonian at low energy, and also non-trivial vacuum degeneracy. For example, fractional quantum states can be described by 2+1 dimensional topological quantum field theories. And I thought TQFT has no local degrees of freedom, but instead it describes topological properties of quasi-particles or string membrane-like excitations in higher dimensions, and their fusions and braiding statistics. In 3 dimensions, these quasi-particles are actual anyons having fractional statistics. And today we are interested in 3D TQFTs, describing physics of such quasi-particles or anyons. And string and M-theory has provided a powerful method to engineer a large variety of quantum systems in various dimensions, as we know. And for example, 6 and 5-dimensional SCFTs are constructed by compactifying M-theory or F-theory on local Calabi threefold. And the world volume theory of M5 rings wrapped on 2D or 3D manifolds engineers a large class of superconformal theories in 4 or 3 dimensions. So such a string or M-theory constructions have been playing very important roles in studies of QFTs. For example, dualities and enhanced symmetries at fixed points has been newly predicted or understood using the constructions in string and M-theory. Or also for some cases, classification of QFTs have been carried out using such constructions. However, previous studies have mostly focused on conformal theories or QFTs with gravity, but we can now ask the question whether string or M-theory can be useful to understand topological phases of matter. So today I'll show you that we can naturally engineer topological theories in M-theory, and presumably such constructions can be used to understand physics of topological phases. So more precisely, I'll introduce the followings. First, I'll introduce a novel construction of 3D TQFTs using M5 rings wrapped on 3 manifold. And second, a relation between modular structures of 3D TFTs and topological invariants of non-hyperbolic 3 manifold. And lastly, the classification of the 3D TFTs based on this M-theoretic construction. So this is my plan in this talk. I've just finished the introduction. Then I will now first review some basics of 3D topological field theories and associated modular structures. And then I'll review another subject called the 3D correspondence. I'll then talk about construction of 3D TFTs from M-theory, which combines these 2 topics. For this, I'll first introduce the construction algorithm of 3D TFTs and then show you some concrete examples. Okay, topological series are low energy effective series of topological phases, such as fractional quantum or liquid in 3 dimensions. One important example of TQFTs is the 3-dimensional Chern-Simons theory. So let me explain some basic properties of Chern-Simons series with the simple abelian theory. So this is the Chern-Simons action for the abelian gauge field A, and here K is the Chern-Simons level. And as you see, there is no metric dependence in this action. So this theory is independent of metric, as we know, but it depends on the topology of space-time. So this theory is a topological theory. There is no gauge invariant local degrees of freedom because of the field equation, dA equals 0. However, this theory has gauge invariant loop operators or Wilson loops wrapped around a closed curve gamma in the manifold. Here, Q is the U1 charge, which is quantized to be integer. This Wilson loop is invariant on the continuous deformation of the curve gamma, so it's a topological object. On the space R2 or S2, since there is no closed circle, we have only trivial Wilson loop. On the other hand, a torus has 2 non-contractile loops. Spatial component of the gauge field satisfy this canonical commutator. And this implies the Wilson loops around the A cycle and B cycles obey this non-trivial algebra, okay? And this algebra, so the loop operators do not commute, and this algebra cannot be realized by a single state. And in fact, we need at least K states. And it turns out that this theory on a torus has K ground state for the level K, okay? And 2 types of Wilson loops act on those ground state in the following way, okay? So we can choose a basis for the ground states such that they become eigenstates of Wilson loops around the A cycle. Then the Wilson loops along the B cycle become creation operators for K ground states. And these actions are compatible with the algebra among the Wilson loops. This means there is a one-to-one correspondence between loop operators and the ground states on a torus. And here, although we discussed only abelian Chern-Simons theory, but this correspondence between loop operators and ground states holds for general topological theories in 3 dimensions. And Wilson loops are actually the trajectory of quasi-particles called anyons, and anyons can have fractional statistics. This is because the amplitude for propagating particle around the loop is modified by the presence of another loop operator like this, okay? When they have non-trivial intersection or linking number. So when anyons exchange their positions, the amplitude receives fractional vector like this. And in 3 dimensions, exchanges of anyons in fact form a representation of braid group. And this braiding statistics among the anyons is very important in 3D anyon physics. And fusions of 2 anyons also characterize TQFTs. So 2 anyons can fuse together and produce another anyon. And here, NABC is called the fusion coefficient. It's a non-negative integer, and it describes, actually, it tells us the fusion rules among the 2 anyons. Okay. And so as you see, these TQFTs are characterized by the fusions of 2 anyons. And for example, in U1 Chern-Simons theory, the fusion rule for anyons is very simple. 2 Wilson loops with charge Q and P fuse Okay?
Asa. Bina.
3.
Is there a question?
No, like 3.
I think someone's just not muted.
Oh, okay,
Just
okay.
continue. Yeah, I'm muting them.
Okay, so yeah, two Wilson loops with the charge Q and P can fuse to a Wilson loop with the charge Q plus P. For non-abelian theory, fusion rule is a bit complicated. For example, in SU2 Chern-Simons theory at level 2, the fusion rule is given by this rule. And here 1, 2, 3 means the 1 to 3 dimensions or dimensional representations of SU2 symmetry. And as you see, the fusion rule is simply the decomposition of a product of two SU2 representations. But higher dimensional representations are truncated because they are screened by the flux. Anyway, annual physics is described by their braiding statistics and fusion rules. A mathematical framework describing the physics of anyons is called unitary braided fusion category, or UBFC. And objects in UBFC are the anyons, including vacuum or trivial anyon, and other non-trivial quasi-particles and their charge conjugations. Anyons have non-trivial fusion rules determined by the fusion coefficient NADC, and charge conjugation and quantum dimensions have these properties. And arbitrary braidings of multiple anyons can be obtained by so-called F and R matrices. And UBFC is also characterized by its modular structure, including S and T operators. And S and T operators are generators of the modular group acting on the Hilbert space of the ground state on a torus. Here, S is the action exchanging A and B cycles of the torus, and T is the then twist. The corresponding S and T matrices are unitary matrices satisfying the following modular relations. Here, theta A and HA denotes the topological spin of the anyon state. And fusion rules can be computed from the S matrix using the Verlander formula like this. Okay, so this is the review for the unitary braided fusion category. And in a topological theory, the modular S matrix is the partition function on a 3-sphere with a Hopf link of 2 Wilson loops. And the T matrix is a diagonal matrix given by topological spins of anyons. And these modular matrices, S and T, together with the chiral central charge C minus, for the boundary to the theory are called modular data. In particular, when S matrix is non-degenerate, the UBFC is called unitary modular tensor category, or UMTC. And UMTCs describe 3D unitary bosonic TQFTs or non-spin TQFTs. In this case, the central charge of the boundary to the CFT can be computed from the quantum dimensions and topological spins. And importantly, it's known that the UMTCs or bosonic TQFTs can be fully characterized by only modular structure. So the modular structure is quite important topological data for 3D TQFTs. And in fact, classification of UMTCs have been carried out based on their modular structures in these papers up to certain length. Okay, let's now switch the topic to 3D correspondence. So let's consider 6-dimensional 2,0 superconformal field theory of AM-1 type that describes the low energy theory on world volume of M5 rings. We'll compactify this theory on a 3-dimensional manifold M3 while preserving n equal to supersymmetries in the remaining 3 dimensions. Okay. Then taking the small volume limit of the internal manifold M3, we can engineer a 3-dimensional n equal to supersymmetric theory, which we call Tn of M3 on X3. the space-time X3. On the other hand, we have complex Chern-Simons theory on the internal three-manifold M3. And in this compactification, the theory T of M3 is determined fully by topology of the internal three-manifold M3. So there is a correspondence between the physics of T of M3 in the 3D space-time and topological properties of the internal geometry M3. This is called 3D correspondence. In particular, various supersymmetric partition functions of the space-time n equal to theory are the same as the partition functions of complex Chern-Simons theory on the internal three-manifold. So supersymmetric partition functions can be obtained from some topological invariants of M3. In this talk, we are particularly interested in the case where the theory T over M3 in this supersymmetric side becomes a topological theory. There is a systematic algorithm to construct an effective theory flowing to the T over M3 theory at low energy. This algorithm was proposed by Dimofte-Gaiotto-Gukov in 2011. We call this algorithm as DGG construction. So let me briefly review this construction. So the effective 3D n equal to theory, or TDGG, can be constructed in the following way. So let's start with the ideal triangulation of the internal three manifold with a torus boundary, or not complement of three sphere. And it's known that all such three manifolds can be triangulated into multiple tetrahedra. And here, tetrahedron is a basic building block of the three manifold in this decomposition. And we glue together, they are glued together along the triangular faces. So to build a 3D n equal to field theory, we assign to each tetrahedron n equal to chiral multiplet. And the chiral multiplets are glued together by superpotentials or gaugings given by some gluing rules specified by the gluing rules of the tetrahedron. And after gluing all these chiral multiplets, we will finally get TDGG theory for the three manifold M3. Then the claim is that the TDGG will flow to the theory T of M3. And this is the DGG construction for given three manifold. So one of the simplest non-trivial example is the theory of the figure in knot. Figure in knot complement. So this is a three manifold constructed by a three sphere with a torus boundary along the figure in knot labeled 4,1. And this three manifold can be minimally triangulated into two tetrahedra. And by DGG construction, the corresponding 3D theory has two n equal to chiral multiplets, and they are glued together by gauging the diagonal U1 symmetry with a Chern-Simons coupling. So this n equal to gauge theory is the effective theory flowing to the world volume theory on 2 and 5 lanes, wrapping the figure in knot complement. And also this theory has enhanced SU to flavor symmetry, and we'll use this enhanced symmetry in the next slide. We can also construct the effective field theories for closed three manifold. So in the previous slide, we saw the not complementary three manifold, but we can also consider closed three manifold without boundary using DGG construction. Okay, general closed three manifold can be constructed by so-called dense surgery prescription. And let me give you one example. It's the closed three manifold given by dense surgery of the figure in knot complement. More precisely, we first prepare a figure in knot complement, and we glue a solid torus to the torus boundary along the knot with a slope P. As we saw, the figure in knot complement can be triangulated into two tetrahedra. So we now glue them to a solid torus with the slope P. And here slope is roughly the choice of shrinking cycle on the torus boundary in the gluing procedure. And in DGG construction, gluing a solid torus with slope P corresponded to the gauging, the flavor symmetry associated to the knot, okay? So in this case, we have SU3 flavor symmetry, as we saw in the previous slide. But in fact, only SO3 is assigned to the knot. So we will gauge SO3 subgroup of SU3 flavor symmetry with the Chern-Simons term at level P. Then this is the effective theory flowing to the M5 range theory, wrapping this closed three manifold. In particular, sorry?
They sort of kept reviving the thing, but also it's like
gauging. So you gauge an SO3. Is gauging, does gauging SU3 have a geometric meaning?
SU3 doesn't, as far as I know, SU3 doesn't have geometric meaning. It's kind of accidental symmetry enhancement.
I see.
In geometry, in particular along this knot, you will see only SO3.
Mm-hmm.
So once you gauge this SO3, which is subgroup of SU3, then the flash is, so there will be no remaining flavor symmetry anymore. So in this closed three manifold, you will see no flavor symmetry.
Thank you.
Thank you for the question. And in particular, when the three manifold is hyperbolic, then the 3D theory TDGG of M3 always flows to a conformal theory at low energy. So for example, big N complement, and this type of closed manifold, when the P is greater than 4, the corresponding TDGG theory will flow to the conformal theories. Okay. In this talk, however, we are not interested in such a hyperbolic three manifold leading to SGFTs. We are rather interested in geometric construction of 3D TQFTs. So we will now focus on non-hyperbolic three manifold, in particular closed non-hyperbolic manifold and associated 3D theories.
All right, Hee-Cheol, could I ask a question?
Okay, sure.
And let me know if my mic's acting up or something. So I thought there was some received wisdom that this DGG construction only flows to a sector of the full M5 frame theory. Is that accurate, or what's going on with that?
Yeah.
So, yeah, is that accurate? Sorry, go ahead.
Yeah, that's true. So DGG construction, as far as I know, only captures some subcomponent in the modular space. In particular, in the geometry, it captures only irreducible flat connections, but actually we can have abelian flat connections, but it's not captured in the TDGG theory.
So that arrow saying the RG flow from DGG to TN, that was just like an approximate arrow or something?
Yeah, only the conformal sector captured by the superconformal field theory from the DGG.
Okay, great. And just
but in this talk,
okay,
sorry. Yeah, in this talk,
sure.
I only discuss this sector captured by irreducible flat connections in geometry.
Okay, and when you say a non-hyperbolic manifold, does that just mean a manifold that's not hyperbolic, or is there some more technical condition like Thurston geometrization or something for no hyperbolic components?
So image it's non-hyperbolic. So locally the curvature has non-negative. So curvature is non-negative.
Oh, I see. Okay.
Yeah. Thank you. Okay. Is there any question? Okay, let me now explain how to obtain 3D topological phases from M theory. So we are asking the question whether we can engineer 3D topological phases by compactifying M5 rings on certain type of three manifold. So by simply generalizing the previous 3D correspondence. However, as we saw, hyperbolic manifold in 3D correspondence always give superconformal theories. So we cannot use a hyperbolic manifold. So instead, we will now use non-hyperbolic manifold. And I'll now argue that we can engineer 3D TQFTs by wrapping M5 rings on a special type of non-hyperbolic string manifold. And moreover, the theory TDGG from DGG construction for this non-hyperbolic string manifold will give an effective n equal to supersymmetric theory for the resulting topological theory. So I'll basically show that the 3D correspondence and DGG construction can be generalized for 3D topological phases. And also for simplicity, I'll only focus on 2 and 5 rings wrapped on J-part fiber the 3 manifold without boundaries. So our claim is the following. So we can consider a 3D theory, T of M3, from a non-hyperbolic string manifold M3, and we claim it has a modular structure if the SL2C Chern-Simons theory living on M3 satisfies the following 2 conditions. First, it has non-empty but finite number of irreducible flat connections. And second, all of such irreducible flat connections are gauge equivalent to SU2 or SL2R flat connections. So I'll explain what irreducible flat connection means in a few minutes. And furthermore, if the theory T of M3 has no emergent or accidental abelian global symmetries, then we claim this theory T of M3 becomes a topological field theory. So this claim is basically motivated by the fact that for such non-hyperbolic string manifold satisfying these 2 conditions actually has a superconformal index, has a trivial superconformal index. More precisely, the theory engineered by DGG construction for such non-hyperbolic string manifold has trivial superconformal index. And the superconformal index over 3D n equal to theory is defined in this way. So it's counting the number of BPS states living on S2, and all BPS states captured in this index are graded by their R charges and spins. So they are graded by the fugacity Q for the R charge and spin. And this means this superconformal index is given by an infinite power series of the fugacity Q in any non-trivial CFT. However, if a theory has a mass gap, then this index will become 1 because only the ground state in a gapped system can contribute to the index. But the index can also be 0 if supersymmetry is broken. So we have 3 cases. I'll now show you that the superconformal index of TDG. Okay.
A question?
Yes.
Is the R charge quantum numbers integral? Are they, or is there a way to see this?
Sorry, you mean the R charge is integral or not?
Yes. Are the R charges integers?
Yeah, here R charges are integers. R charges for the states are integers.
Is there a way to see that easily?
From this definition.
So may I answer the question? So this is a SO2 subgroup SO5 R symmetry in the 60. So this is compact. So this is alpha is already quantized.
Yeah. So if we consider compactification from 6 dimensions, they are quantized. But in general, for general n equal 2, I have no clear argument to say this R charge is quantized to be integer for series.
So is it then that you can always, there's always a clear normalization to make sure that the quantization is integral? So
yeah. In our case, because in our case, all the 3D theories are coming from 6 dimensions and compactifying them on 3-dimensional manifold after doing some topologically twisted, then we know this R charge is identified with the SO2 subgroup of SO5 R symmetry in 6 dimensions. And so it's quantized in that case.
Thank you.
Okay, yeah. Okay, yeah, so I'll now show you that the supercomponent index of TDGG for the three manifolds satisfying these two conditions become one, and therefore the 3D theory would become a topological theory. In 3D correspondence, the supercomponent index of T of M3 is given by the partition function of SL2C Chern-Simons theory on the internal three manifold with the Chern-Simons level K equals 0. And using this relation, we can write the supercomponent index as the path integral of the Chern-Simons theory put on the internal three manifold. And this partition function can be computed perturbatively in the small coupling H bar. And in small H bar limit, this partition function can be written as a sum of SL2C flat connections on M3. And here alpha labels the flat connections. And the flat connections are nothing but the solutions to this equation. Okay. And here in the exponent, the first term is the classical term, and second term is the one-loop term. And mathematically, the classical term, they are basically the mathematical invariant of the three manifolds. And this second term is called the Ray-Singer-Reidemeister torsion. And we have a higher loop corrections, but we are not interested in them. And this perturbative limit or small h bar limit is the same as Q goes to one limit. So for CFT, this index diverges in this limit actually. And the divergence is basically captured by this classical term. Okay. And for TFT, this divergence must vanish. So if it's the case, then this partition function will become finite in this limit Q sent to 1. And this classical part or the divergence term can vanish only if all flat connections A alpha are either SU2 or SL2R flat connections up to conjugation. Therefore, for the TDGG theory flowing to a TQFT, the flat connections on the corresponding three manifold must satisfy this reality condition, okay, because of this property of the supercomponent index. So if we assume that the internal Chern-Simons theory has a non-trivial irreducible flat connections, then the space-time 3D theory has a non-zero supercomponent index. Their procedure is unbroken if there is a non-trivial irreducible flat connection. Moreover, if the flat connections are real, namely SU2 or SL2R flat connections, then as we saw in the previous slide, the supercomponent index is finite in Q to 1 limit. Therefore, it cannot be the index over SCFT. Therefore, from the property of the supercomponent index, if the Chern-Simons theory on the three manifold satisfy these two conditions, then 3D space-time theory, T of M3 has a supercomponent index 1. So it would be a topological theory by the property of the supercomponent index. So this is our criteria for non-hyperbolic three manifold associated topological theory via the 3D correspondence. But there is one subtle issue. For example, our criteria hold only if the partition function of the internal three manifold agrees with the supercomponent index of the T of M3 theory. This is in general correct. However, if there exists some accidental abelian global symmetry, which is not visible in the 3D manifold or in the compactification of M5 rings on the three manifold, then the supercomponent index can be different from the partition function of the three manifold because this accidental abelian symmetry can mix with the asymmetry of the 3D n=2 theory. We know some of such examples, but in the following discussion, we'll assume that we do not have such accidental symmetry. Before I show you concrete examples, let me first explain the map between physics of 3D topological series and geometry of non-hyperbolic free manifold. Let me first introduce the map between flat connections in geometry and anyons in 3D TFTs. In Chern-Simon's side, SL2C flat connections on M3 can be characterized by holonomy matrices along the one cycle in M3. So we'll use both A alpha. So this rho alpha is the holonomy matrix, but so there is a map between flat connection and holonomy matrices. So we will use both A alpha and rho alpha to denote flat connections. And this flat connection is said reducible if all holonomy matrices commute each other. Otherwise, it's called irreducible, but we are only interested in such irreducible flat connections which do not commute each other. And in 3D correspondence, irreducible flat connections on three manifolds are mapped to the beta vector in T-DGG theory. And this fact actually implies that when T-DGG flows to a TFT, the beta vector corresponds to ground state on a torus. So they are mapped to anyons. Therefore, we can say that an irreducible flat connection, rho alpha on M3, is actually mapped to the anyons in 3D TFT of M3. So this is a map between the flat connection and anyons. In 3D TFT, anyons are quasi-particles and they are basically line operators. And in M-theory construction, such line operators come from M2 branes ending on M5 branes, between M5 branes and wrapping one cycle A inside three manifold like this cartoon. So M2 branes stretched between 2 and 5 branes can wrap around the non-shrinking one cycle in a non-hyperbolic three manifold, and it becomes a one-dimensional line defect in 3D space-time. It therefore becomes an anyon if the 3D theory flows to a topological theory. And this fact and the correspondence in the previous slide actually implies that there is a natural map from the irreducible flat connection to the M2 brane state labeled by the cycle A and representation R of SL2 symmetry. Okay. And this map is important when you compute the full modular ST matrix from geometry, but I will not explain the details. So let me give you an example. Okay, one famous non-hyperbolic manifold is the Seifert fibered manifold. And when it has three fibers, it's labeled by three rational numbers, P1 to 3 and Q1 to 3. And here P, I, Q, I are integers and they are coprimes. So this is a Dancer's representation of the Seifert fibered three manifold with three fibers. The fundamental group of this manifold is described by four components, X1 to 3 and H, and they satisfy the following equations. So this is the fundamental group of this Seifert fibered three manifold. And doing this fundamental group, we can now compute the flat connections of the Chern-Simon theory on this manifold. The flat connections are described by the homomorphism from the fundamental group to the SL2C gauge group up to conjugation. So taking Xi and H as elements of SL2C group, we can now find the flat connections by solving these equations. Okay. So for given Pi and Qi defining the Seifert fibered manifold, we have an algebraic equation for four SL2C matrices Xi and H. And one can solve this by putting them into computer or mathematical. So for example, for Seifert manifold with 3, 3, minus 4/3, we found three irreducible flat connections. Okay, these are three solutions to these fundamental group equations. Okay. And they are all real. So it means holonomic matrices for all the one cycles in this three manifold are real. So this geometry satisfies our criteria, and therefore we expect that the 3D theory engineered by M5 brains wrapping on this manifold will flow to a topological theory. And also the three irreducible flat connections in this manifold M3 are now mapped to the three anyons in the topological theory. And indeed, this geometry engineers, as we will see, the 3D Ising TFT having three anyons. We'll come back to this example in a few minutes. And once we identify the anyons as flat connections on the three manifold, we can obtain modular structure from the geometry. Here we'll now use the fact that the partition function of a general 3D TFT on 3D Euclidean space given by degree P bundle over genus G Riemann surface can be written in terms of the modular matrices S and T in the following way. Here alpha is the anyon type. And quite interestingly, we have a similar formula for the partition function of the n equal 2 supersymmetry theories like this. When they are it's topologically twisted on the same space. And in this case, the sum is over all beta vector of the supersymmetric theory. And here, H is called Handel-Gluing operator, and W is the twisted superpotential, and F is called fibering operator. Okay, and this formula was computed in this paper using the supersymmetric localizations. And furthermore, in the 3D correspondence, we have the following maps for the 3D n equal 2 series with for the n equal 2 series for three manifold with the trivial homology group. And first one is the beta vector corresponding to SL2C flat connections, as we saw already. And then the Handel-Gluing operator and fibering operators are mapped to the torsion and the classical Chern-Simons action. And this map generally holds for the both hyperbolic and non-hyperbolic three manifold when P is even. And this map implies the partition function of 3D theory T of M3 can be written in the following way. Okay. And by comparing the partition function for the general 3D TFT on this manifold with this partition function of T over M3, actually we can find the map between the the topological invariant of the three manifold and S and T matrices. Therefore, for TFT of M3, we can derive the following map between three manifold invariant of M3 and modular data in the 3D TFT. The first one is the irreducible flat connection, which is mapped to the anyon type, as we discussed. And the torsion in the three manifold is mapped to the S0 alpha component of the S matrix. And the classical Chern-Simons action is mapped to the T matrix. So this is the summary of the 3D correspondence between 3D TFTs and internal non-hyperbolic three manifold. For the non-hyperbolic three manifold satisfying the condition 1 and 2 given here, we expect that the M5 range multi-volume theory wrapped on such non-hyperbolic three manifold will flow to 3D TFTs. And in this correspondence, the M2 brains wrapping on cycles associated to the real flat connections become anyons in the 3D topological theory. And this table is basically the dictionary between the topological data in the 3D TFT and invariant of non-hyperbolic three manifold. Again, the anyons correspond to irreducible flat connections, and T matrix is the classical Chern-Simons action, and S0 alpha is the torsion of the non-hyperbolic three manifold. And we can actually compute the flat S matrix by using the map between flat connections and the loop operators. And lastly, the central charge of the boundary 2D CFT in this 3D topological theory can be obtained from the classical action evaluated on the flat connection corresponding to the vacuum state. And more precisely, the chiral central charge modular half can be computed from three manifold. And here modular half comes from the phase ambiguity in the partition function. One remark is here that for unitary TFT, S and T matrices are all unitary. And in particular, the absolute value of the component S00 must be smaller than other component S0 alpha. But we found some examples that have unitary S matrix, but do not satisfy this last condition, this last inequality actually. But such examples have, interestingly, non-unitary modular structure, but we checked that they actually flow to SCFTs or SGFTs, not TQFTs.
Sorry, can you remind me what rho naught is? That's some
Sorry?
Can you remind me what rho naught is? That's some irreducible flat connection that's particularly special. Which one is that?
Yes, this is a irreducible flat connection corresponding to the trivial anion.
So
vacuum state.
So could you describe what that is as an irreducible flat connection?
So actually this irreducible flat connection has some algebraic equation. So we can identify this one using some algebraic equation, but that I didn't write down in this slide. But it's basically saying that the partition function, this one, when G is 1 and P equals 0, becomes the three-sphere partition function, which is actually S00 component of the S matrix. By solving that one, you can actually determine this special irreducible flat connection corresponding to the vacuum state.
Okay, I see. Cool. Awesome. Thank you.
Okay. Yeah. So there is a systematic way to fix this special flat connection by using the map between the geometric invariant and the partition function of the TQFTs. Okay, let me give you some concrete examples. So one of the simplest example is the 3D theory T of M3 on the J-pod 5 of the 3 manifold S2 3, 3, minus 4 over 3, which we met before. And as we discussed, this geometry has 3 irreducible flat connections, and they are all equivalent to SU2 or SL2C flat connections. And therefore, according to our criteria, this theory will flow to our topological theory. And indeed, we found that this theory, T of M3, will flow to the 3D Ising TFT, having 3 anions, 1 sigma and per psi, given having the following fusion rules. Okay, and these 3 flat connections become these 3 anions in the Ising TFT. And to find the modular structure, we need to compute the Chern-Simons action and torsions of the 3 manifold evaluated over the 3 irreducible flat connections. And actually, Rojansky provided very nice formula to compute these functions when the flat connections are all known. And we used this formula and computed Chern-Simons action and torsions from these irreducible flat connections. Okay, and lastly, by using this topological invariant of 3 manifold and using our dictionary summarized in the previous table, we can easily compute the following modular data. So here, central charge is given by half, and the topological spins for 3 anions are 0 and 1/16 and 1/2, and S matrix is given by this. Indeed, this modular data perfectly agrees with the modular data of the 3D Ising TFT. So we see this computation of the modular data from geometry as a concrete check for our 3D correspondence between the 3D Ising TFT and the J-pod 5 of the 3 manifold. And in addition, we can, in fact, construct the 3D n equal to supersymmetric QFTs, QFT that flows to this Ising TFT by using DGG construction. And it's known that this J-Pulse 5 of the 3 manifold is topologically the same as the 3 manifold obtained by the figure in knot complement and then filling of the torus boundary with the slope P over Q equals 3, which is the geometry we saw before. And as I explained, the DGG construction for this geometry is the U1 gauge theory with the Chern-Simons level 0 coupled to the 2 chiral multiplets. And then we gauge the SO3 subgroup of the global symmetry with the Chern-Simons level 3. So this 3 is this slope 3. Okay. So this n equal 2 gauge theory is an effective theory that flows to the world volume theory of 2 and 5 rings wrapped on this non-hyperbolic 3 manifold. And we expect this theory flows to the Ising TFT at low energy. And one can easily check that the supercomponent index of this theory is indeed given by 1. And moreover, modular data can be also computed using this n equal 2 theory in 3 dimensions, and they agree with the geometric result in the previous slide. In the same way, we can construct a large number of 3D TFTs, and actually we could construct all 3D unitary bosonic TFTs up to rank 4 just using 2 and 5 rings compactified on the J-5 of the 3 manifold. So this is the classification table for the unitary modular tensor categories found in these 2 papers. The first column denotes the name of the UMTCs. So this is the name. And second column denotes the 3 manifold corresponding to the TFTs. So here I use the notation introduced by the Xiaogang Wei. So unitary modular tensor category is labeled by their rank, number of anyons, and the chiral central charge, and also their spins, spins of the anyons. So each row in this table corresponds to an independent TQFT. And for example, at rank 2, we have 2 distinct TQFTs. One is called the Fibonacci TQFT, and another one, Fibonacci MTC, and the second one is the Semyon MTC. And Ising MTC is here at rank 3, and the famous K-type Tori code is here at rank 4. And they all have the geometric realization in M theory. So surprisingly, up to rank 4, all TQFTs classified in the other literature are realized in our M theory construction. So it may be possible that our M theory construction can realize all 3D topological theories. But for that, I think we may need to generalize our construction by increasing the number of M2 branes. Here we just use the 2 and 5 branes, but we can increase the number of M5 branes. And also we need to involve other types of non-hyperbolic manifolds, 3 manifolds in our constructions. But with such generalization, probably all the 3D topological field theories can be realized in M theory. Okay, let me summarize my talk. So we proposed a new correspondence between 3D topological phases and non-hyperbolic 3 manifold based on geometric construction of 3D topological phases using M5 rings wrapping non-hyperbolic 3 manifold. And in this correspondence, anyons in the 3D TFTs come from M2 rings wrapping 1 cycles in the internal 3 manifold, which are characterized by irreducible flat connections in the Chern-Simons theory on 3 manifold M3. And we found an explicit map between modular data in 3D TFTs and topological invariance of non-hyperbolic 3 manifold. And lastly, all bosonic MTCs up to rank 4 are physically realized in M theory. And their effective n equal to supersymmetric QFTs can be obtained by DGG construction. We can now think about the following problems. For example, first in our paper, we mostly focused on realizing unitary modular tensor categories, which are basically bosonic TFTs without symmetries. But there are actually fermionic TFTs and also TFTs with unsighted symmetries. For these series, we need to consider probably three manifold with non-trivial H1 or the G2 homology group. The 3D correspondence for the three manifold with the non-trivial homology group was discussed in this paper. And in our paper, we used their result and constructed some of such TFTs using non-hyperbolic three manifold with non-trivial H1. But in general, I think we need to further generalize our construction to involve more M5 rings and other non-hyperbolic three manifold, and also three manifold with boundaries. And with these generalizations, we can possibly realize all 3D TFTs in M theory. It's also an interesting problem to find a new invariant for characterizing 3D TFTs beyond the modular data. As discussed in this paper, the modular structure is actually not enough to fully distinguish modular tensor categories or topological quantum field series. So by studying geometric invariance of non-hyperbolic three manifold, we may be able to find new interesting invariants for 3D TFTs. Another interesting question is if we can classify all 3D topological phases by using our geometric construction. And also it would be interesting to find the geometric interpretation of phase transitions between topological phases. And lastly, generalization to higher dimensional TFTs using the M theory construction or string theory construction would be very interesting problem. Okay, let me stop here. Thank you very much.
Thank you very much for this really nice talk. I think we can all clap here.
Thank you.
Other questions from the audience? So let me actually start asking a question. So you just mentioned at the end to go to a higher rank and to actually have a sort of generalization to all 3D topological phases potentially. Is there a way to characterize which M3s, non-hyperbolic M3s, give rise to distinct topological phases? So for example, if you have two three manifolds, can they give rise to the same TFT? And how would they be related, for example?
Which example?
So if you have, is it possible that two non-hyperbolic M3s can still lead to the same TFT? And is there a way to sort of characterize the class of?
Actually, we found the infinite non-hyperbolic three manifold leading to a single MTC. So there is very high degeneracy in the geometric side. The problem is unless you compute the S and T matrices, we couldn't distinguish whether this non-hyperbolic manifold lead to some particular MTC or not. So at this moment, we don't know how to, so just by looking at just the geometry, we don't know how to identify the corresponding MTC before we compute the S and T matrices. So at this moment, we don't have, for example, new invariant characterizing the two distinct modular tensor categories, though they have the same modular data. But it's a very good question. So we have to develop some method to first distinguish the non-hyperbolic manifold or associated TFTs just by looking at properties or invariant of the non-hyperbolic manifold before we compute the modular structure.
Okay, thank you. Any other questions?
Yeah, but interestingly, we have an infinite number of non-hyperbolic manifold giving to the same TFT. Yeah.
Ibu, do you have a question?
I have a question. Is there a simple way to see the sort of discrete symmetry that exists in these different phases?
Discrete symmetry, you mean the zero form and one form symmetry in TFTs?
Yes. Yeah.
Actually, so this non-trivial H1 is associated to the one-form symmetry of the resulting TFT, which was discussed in this paper by Sakura, actually. So once you know this H1, you can identify the one-form symmetry, and by gauging or choosing some particular polarization, you can also identify zero form. But actually, you can have more symmetry than the symmetries which you can identify just H1. But in the IR theory, in IR TFT, you can actually have the bigger symmetry.
But this
that
bigger
you see from this non-trivial H.
But this bigger symmetry, you cannot, or you don't have a systematic way to read from the geometry.
At this moment, I don't know. Yeah, at this moment, I don't know how to identify the bigger symmetry just by looking at the geometry.
Thank you.
Yeah, are there any other questions?
Can I ask something?
Sure, Sama.
So, so you show that for one case you were able to identify the n equal to theory, was this Stottery gauging with Simons of the figure 8 theory. So in general, how, I mean, can you, I mean, do you have an algorithm to guess what is the theory, the n equal to effective TFT?
Actually, we just use digit construction. So for the given three manifold, we triangulate it by the tetrahedron, and we glue tetrahedron together to form a three manifold. So by just converting this data to the n equal 2 data, by combining all the n equal 2 chiral multiplets, following the rule given by the gluing rule of the tetrahedron by introducing superpotentials and gaugings, and we can construct, in principle, we can construct the 3D n equal 2 theory flowing to the TFTs.
So even if it is not hyperbolic, the construction is the same. You use
right. Yeah.
Can I ask a question?
Sure.
So do you expect anything new to happen from if you take 1,0 instead of 2,0?
Yeah, sure. But problem is at this moment, we don't have a very systematic way to analyze the 3D series if we use 1,0 theory.
But from
so if you use 1,0, then the problem is how to compactify this theory on a three manifold. You are talking about 3D TKFT or 4D TKFT?
3D.
Yeah, 3D, then you have to compactify this theory, 6D theory on a three sphere. Then you need to do the topological twist along the 3 dimensions, which is wrapped to the three manifold. But for 1,0, you have just SU2R symmetry. So topological twisting will not leave any supersymmetry after this compactification. So it's a bit hard to control.
Okay, thank you.
So I don't know.
You could also ask if you had 2,0, but you do the twist that gives you 3D n equals 1. And now you pick an M3 that's not hyperbolic.
Oh, yeah.
I mean, you don't have a
that
superconformal. There's no superconformal index, but it's a 3D n equals 1 theory. Is there another TFT sitting there for certain M3s, right? I think it's a similarly complicated question, I guess.
Yeah, it's a great idea to extend this onto 3D n equal 1.
I don't know how you would even check, right? Because I don't think you can
right.
calculate
We can just compute the between index, but
which is not, I think, enough. So
yeah.
But will you have a geometric way to compute what the TQFT will be?
For n equal 1?
Right, yes.
Maybe Sarah knows. I don't know. Or Sakura.
I think all we know is for special cases, the written index, but I don't think that's enough.
It's not enough, yeah.
So are there any, I don't see any other questions. Actually, there's a question in the chat. So Feng Shuan was asking, is it possible to embed some non-hyperbolic space into some G2 manifolds? Okay, so I think this is exactly the question this reading
You,
question.
yeah.
Okay.
Yeah.
So, I
So you
think
deleted
we-
N equal 1.
Yeah, that's it. Yeah, so I think this
Yeah.
answers that. Okay, let's thank Hee-Cheol again for this really great talk, really interesting results. So you can unmute
Thank you very much
yourself
for
and
the
start. Yes.